Hello. So, we have been on this topic of magnetic particle testing, and in last few lectures we have seen several aspects of this particular technique and learned about them. In today's lecture, this will be the fifth one and the concluding lecture on this particular topic. So, let us see what we have done so far quickly. So, we have talked about the magnetizing methods and then how the particles are applied, what kind of particles you have and so on. Okay. And we have also seen depending on the condition of the surface or the kind of part you have. Okay. So, depending on that you choose different kinds of powder, either wet suspension, and in the wet method itself we saw there are different kinds of suspensions depending on what is the part being examined, and then depending on the surface condition we saw that either dry or wet particles can be applied, and there are different methods by which these are applied. Okay. Yeah, so today finally we will see how the inspection is being done, which is the final step. So, we have started from, again I will go back to this, we have started from this, and then finally once the particles are applied, then we do the inspection. Okay. So, let us talk about this today and few more things. So, inspection, as you would have seen in the demo video that I showed you in the last lecture, you could do it in a well lit area where you have enough lighting. So, that is for the normal particles that you use, okay, what you saw in the video, which could be either dry or wet particles. So, that is what you do when you have normal either wet suspension or dry powder. You take it to an well illuminated area and then see if you can see some visible indications of the surface flaws. Okay. The other thing that you can do in this case, as you would have seen in case of dye penetrant testing, in this case also you can do this fluorescent inspection. So, in case of dry powder, if you remember, I said that these powder are many a time coated with color. They can also be coated with a fluorescent material. Okay. So, in that case you would be able to do this inspection under UV light, and the defects and flaws, if they are there, then these flaws will glow in a dark room when they are exposed to UV light. Okay. So, this is something that we have seen before also in case of dye penetrant testing, and I told you that when a fluorescent material is exposed to ultraviolet light, then they emit light in the range of yellow to green in that wavelength, and you will see these defects and flaws glowing either in yellow color or green color or something in between them. Okay. So, that is what happens when you do this fluorescent particle inspection. So, these are primarily dry powder coated with a fluorescent material. So, in this case you need to do the inspection under UV light. And if there are flaws and defects, as I said, they will glow, they will fluoresce due to this exposure, and that is how you will get the visible indications of the flaws. Okay. So, these are the two ways of inspecting the part finally. But there is one more thing remaining which apparently may not look like a part of this particular technique, but once this inspection is over, okay, your part is still magnetized. Okay. So, that is something which is not desirable, because it could be a component which will be used, okay, if there are no flaws. So, in that case, if it is still magnetized, so that magnetic field of the sample of that component can affect its function when it is used along with some other parts in a particular system. Okay. So, the last step in this case then should be to demagnetize the part, okay, before you wind it up. So, that is the last thing that you need to do. Okay. If you do not demagnetize, as I said, there are problems. So, let us see what could be the possible difficulties if you do not demagnetize the part after you do the inspection. So, if not demagnetized, then let us say this is something a semi finished kind of part which has to be further machined to give the final size and shape. Okay. So, in that case it can affect the machining. So, this we are talking about if not demagnetized, what could happen. Okay. It will affect machining by causing the chips to cling to the surface because of the magnetic field. The machining chips which are generated will stick to the surface, which will affect the machining operation. So, these chips will cling to the surface. Then let us say the part has to be used in some kind of electronic system or some electrical system, then it can interfere with some other electronic components because of the presence of the magnetic field again. Or if it is used in close proximity of some electronic component, there again it will affect the electronic components because of the magnetic field. And let us say this part has to be welded for some reason to give it a shape or whatever reason, if this has to be welded, and if you use an arc welding process. Okay. So, in that case this will create the magnetic field of the part will create something known as arc blow due to the presence of the magnetic field. This is arc blow is nothing but movement of the arc or the filler material which is used for welding Okay, so this movement of either the arc or the filler material is due to the presence of an additional magnetic field which is in the part. Okay. So, this is arc blow again is not desirable. If the arc moves, then your welding will be improper. It will create some kind of uneven welding and things like that. So, there again this presence of the magnetic field on the part is not desirable, and you need to demagnetize the part before you can weld it if you plan to use an arc welding process. Then it can also cause abrasive particles to stick to the surface. Let us say in a part like bearing, and this will increase the wear. Okay, so these are the different things which can happen if you do not demagnetize the part, and therefore, as I said, as a final step you need to demagnetize the part before you close this process. So, let us see how you can demagnetize and what methods are available for doing this. So, there are two ways by which you can do it. One is you can heat it above the Curie point or the Curie temperature. This is a temperature, as you might know, above which a ferromagnetic material loses the magnetism, and the reason behind that is the magnetic domains that you had, which were aligned in the direction of the field. If you remember, we have talked about this. When you apply a magnetic field, the magnetic domains in a ferromagnetic material align in the direction of the field when you reach saturation. So, when you heat this ferromagnetic material, as you increase the temperature, these domains again will misalign because of the atomic vibration that happens due to the temperature, okay, or due to the heat. So, due to these atomic vibrations, as you keep on increasing the temperature, these magnetic domains will again get misaligned, and above a particular temperature, all the domains will again be oriented randomly, like how they were in the beginning when the part was not magnetized. Okay. So, this is how hitting it above the Curie temperature will demagnetize it. Okay. But for this you need to have heating arrangement furnaces and all that, because this temperature can go high. For example, for carbon steels, this Curie temperature is around 770 degrees Celsius. So, you need a furnace, a heating arrangement which can heat the part to this kind of temperature. Okay. So, if you could afford to have a heating arrangement, a furnace, then you can take the part and heat it above the Curie temperature and then demagnetize it. The other way of demagnetizing the part is field reversal. That means, if you know the magnitude and the direction of the field which was applied in the beginning to magnetize the part, then you can apply a same magnitude of field, but in the opposite direction. Okay. So, if you apply the field in the opposite direction, it will go through that hysteresis curve in the other direction, and at some point when it reaches the coercive field, the magnetic flux in the material will become 0. Okay. So, there again in this case knowing the direction of the field helps you. So, this is the another advantage if you know the direction of the magnetic field. Okay. The other advantages we have already seen, like the orientation of the defects with respect to the direction of the field, the visibility of a defect would depend on that. Okay. And the other advantage you have if you know the direction is this, when you finally come to this step, if you had known the initial direction of the magnetic field, then now you can apply the same field, the same magnitude field in the opposite direction, and then at some point when you reach the coercive field you can demagnetize the part. Okay. So, these are the two methods, these are the two ways by which you can demagnetize the part. Okay. So, this is how the process works. Now, finally, let us see what are the applications of this particular method, and then like what we do for every process, we will also see what are the advantages and disadvantages. But before that, one thing that you should always remember whenever you do NDT, not only for this method, but other methods also, are false or non-relevant indications. Which could arise due to various reasons. Okay. So, this may look like a defect, it may give an impression like a defect, but it may not be a defect. Okay. The indications that you see, okay, this kind of false or non-relevant indications, they may look like a defect on the surface, but actually they may not be. Okay. So, while doing NDT, you should be always aware of these kind of non-relevant indications, so that you do not make a false call. Okay. So, let us see for this particular technique for magnetic particle testings, what are the reasons for which you can get you can end up with false or non-relevant indications. Accumulation of powders at corners where there is a change in the cross section of shape. Okay. So, if the part is not very regular, if there is little bit of complexity in the geometry, let us say around the corners there is a change in the shape or in the cross section. So, along those areas, because of this change the particles may accumulate, and it will look like that this accumulation is because of a leakage field. So, it will give an impression that along those areas there are defects, but actually the reason is the change in the cross section or the shape, not really the presence of a defect. Okay. Then if you have an external magnetic field present around the part, okay. So, there again because of this external magnetic field close to the sample, okay, these can also generate false indications or non-relevant indications. Then if you have sharp corners or edges in the sample or in the part being examined, So, these are the areas where the particles tend to segregate or the particles tend to accumulate. Then you could have these kind of areas also, like thread roots, keyways, fillets. Okay, so, these are the areas where due to this geometry itself the particles would tend to segregate, and then it might look like that around these areas there are defects because particles are getting accumulated over there. Okay. But this is again due to the geometry and not really due to the presence of a defect. Then if you have junctions of dissimilar metals, so this two different materials, two different metals, their magnetic properties are different. So, across this junction, across this interface, the magnetic permeability will change. Okay. So, due to the change in this magnetic property across the interface, again you could end up with some non-relevant indication. So, you should be careful when you have this kind of dissimilar metal joints if you examine them by magnetic particle testing. So, this is due to the difference in the magnetic permeabilities between the two materials. At the junction. Okay. Then if you have subjected the part to some kind of cold working or machining, so it has gone through some kind of plastic deformation due to these processes, and due to that the magnetic permeability can change, and you may end up with non-relevant indications because of this change. Okay. So, there again if you know that the part which is being inspected, if it has gone through a cold working or machining kind of process or some kind of plastic deformation process, there again you should be careful about the non-relevant indications. Then in polycrystalline materials, in polycrystalline metals and alloys, you have a large number of grain boundaries. So, they can also be a source of non-relevant indications, particularly in large grain size material across the grains. When you encounter the boundaries, there could be a change in the magnetic permeability. So, for such materials where you know the grain size could be large, like for example, in castings where the grains are generally large. So, there again you should be careful about these non-relevant indications. Okay. So, these are the different reasons due to which you might end up with non-relevant indications in case of magnetic particle testing. Okay. So, you should be careful about all this when you do this testing. And finally, let us see what are the applications of magnetic particle testing. Okay, so, this can be applied for large castings and forgings for inspecting the surface flaws. Can also be used for long tubular parts. Weld cracks. Then in welding, lack of fusion, which is a welding defect that can be inspected. Then parts like crankshafts or camshafts can also be inspected. Then hollow parts or holes, we have seen this before also while discussing about particle application. If you have hollow parts, what kind of particles you can apply? You can apply a slurry or magnetic paint kind of thing or a magnetic rubber. Okay. So, like holes in thread holes. Then other parts like bearings, hollow cylinders, nuts and pipe couplings. So, these are some of the applications of magnetic particle testing. Okay. And finally, let us see what are the advantages this particular technique offers and if there are any limitations also. This is a very simple process as you would have seen and also cost effective. In terms of the consumables, all you need is some magnetic particles, like you can use iron particles and a liquid which could suspend it. Sensitive to small flaws. And one of the biggest advantage that this process offers is subsurface. You would be able to inspect subsurface in this case, which was not possible in case of other surface NDT methods like dye penetrant testing. So, in this case you can go a little below the surface also. So, you could inspect at the subsurface level as well. So, subsurface flaws can be inspected. Complex parts again is not a problem for this, complex parts can be inspected. And large areas or volume can be easily inspected at a low cost. Okay. So, these are the advantages that this process offers, but like any other process, this will also have its own disadvantage also. So, let us have a look at them. So, this is limited to only magnetic materials. It cannot be used for non-magnetic materials, because the whole thing is based upon magnetism. Okay, that is the major limitation of this process. Particle accumulation in suspension has to be controlled. In the wet process. And if you have contamination, then it can affect the result. Or the sensitivity. And as we have seen, field orientation, that is the direction of the field, and field intensity has to be established. Before inspection. Okay. So, these are some of the limitations that this process has, but nevertheless this is a very useful process again for doing surface and subsurface inspection on magnetic materials. Okay, so this will bring us to the end of this particular topic, and before we close this, let us take a moment to summarize. So, we learned the basic principle of this particular technique. And we saw that it is due to the leakage field at a discontinuity. So, we learned about that. And then we talked about different methods of magnetizing the part. So, in this we saw contact and non-contact methods. And we also learned about the direction of the field depending on the direction of the magnetic current, how the field direction will be, that also we have seen. The next step was particle application. So, there again we saw there are different methods by which the particles can be applied, and then we saw there are two types of particles which can be used. One is wet, which you use in a suspension, and the other one is a dry powder, which can be coated with either a color or sometime it is also coated with a fluorescent material. Okay. And in this case we saw how this wet suspension is applied depending on the part geometry or the type of part. Like we had normal suspension in a liquid, and then we have some highly viscous suspensions for particular applications. like overhead parts and things like that. Okay. And finally, we saw how the inspection is done. When you are using normal magnetic particles either in dry or wet suspension, you do it normally under visible light, or sometime if a fluorescent material is used in a dry powder, then it has to be done under ultraviolet light, that also we saw. So, there are two types of inspection which can be done depending on what kind of particles are used. Okay. And then finally, we saw that once the inspection is done, you need to demagnetize the part, because that is also important. And then we talked about non-relevant indications and the causes for them in this particular technique. And finally, we saw some applications of this method and the pros and cons of this particular technique. Okay. So, this is all we had in this particular technique of magnetic particle testing, and this is all I have for today, and I will see you next time with a new topic. Thank you for your attention.